Hello, you're welcome to today's class. Uh, Welcome from the break, and to all of you that are able to do your assessments, your chapter test and assessments. I congratulate you. Well done. Now we are moving to the second segment of our workshop, our training, and that is from module 11. So 11 to 28. So today I will be looking at module 11, which talks about network communication devices. Okay, and that's what we're going to be looking at today. Now, what are network devices? Network devices are any device that that has a role to play in the exchange of communication between a sender and a receiver. And in most cases, the network devices are grouped into three. We have what we call the end devices. The end devices, okay, that is the end devices here. Now, these end devices are usually the devices that are either the destination, either the source of the message or the destination of the message, like your desktops, your servers, your mobile phones, your IP cameras, your fridges, your any device that that actually receives this message or sends this message is an end device. So the other one is the intermediary devices. The intermediary devices are the devices that that does traffic control, that determine how the traffic is moved, how the traffic is shaped, and things like that. And this include things like your switches, things like your routers. They are intermediary devices. Okay, and see the network media. In this case, it can be cable media, it can be wireless media, all right, or it can be optical media. So these are communication. These are the elements that play key role in communication. Now, the most familiar network devices are end devices, you know, and we said they are either the source of a message where the message is transmitted or generated, or they are like the destination of the message. So to distinguish one end device from another, each one of them has an address. The address is like the IP address, the Internet Protocol address, and actually it identifies uniquely every end device on the network. So it can be able to say who initiates this message and where this message is actually going to. Okay. Now, routers are devices that operate at layer 3 of the OSI model, right? And because routers do two things, they do path determination and they do packet forwarding. So the router also serves as a border at every network. So you see, this is like the central office, and the border into the network is a router. This is the branch office, the border is the router. All right, this is the home office, and the border is a router. So you see, the router actually serves like a border, and all traffic coming into the network goes through the router, and all traffic going out of the network go through that particular same device. So the routing process uses network routing tables. Routing tables is like where all the possible routes to that particular routers are stored. So if you have a router, for instance, this router here is in the internet. This router has on its routing table information on how to get to all the locations that are directly or indirectly connected to it. So routers actually gather this information and update one another, you know, on how best to route their packets. And what they use is usually a protocol. All right. So this protocol is basically a rule that enhances how they communicate the exchange of this information. So, for instance, you have router one here, and you have router two. So, in router one has information about this network, here. Router one has the information stored here. Router 2 has information about this network stored here. That is this block of IP, this network. Router 1 has this network. And then both router 1 and 2 has information about this network. Okay, both of them share information about this network. But you see, router 2 does not have information about this network, and router 1 does not have information about this network. So what happens is that the two routers are going to exchange information. All right, they are going to exchange this information either by the administrator manually adding this information on this router. For instance, on router 1, we add a static route. You can see it here. You add a static route to tell the router that, look, if you want to go to this network from here, follow this line, follow this exit, follow this interface. That is what this configuration is saying. All right. So this one, as you see S here, it means that it was statically assigned. Now you can configure a routing protocol to dynamically inform to populate it in its routing table. So the essence is that if there is a traffic, is a packet that is designated for any of the end devices within this particular network, um, it will go through this particular router, and this router will say, oh yes, I have actually a route on how to get there. All right. So so it uses the routing table to do its routing processes and switching processes. The routing processes is here. All right, this one's here. And what it does is that it checks the routing table or the list to find the possible match to the destination address. And then the switching process is done here. And in that case, it tries to, for instance, if it gets this as the match, what it does is say, okay, how do I forward the packet? So it will tell it, forward it through this interface, or forward it through this interface, or forward it through this interface. So the switching process takes place here. So those are like the two primary functions of the router. So after the router has determined the exit interface using the path determination, the router must encapsulate the packet into the data link frame. So you see the encapsulation that we're talking about is the process of adding header information from the top to the bottom. That's from application layer, presentation, session, transport, network, data link. So adding this information on those steps. So in the network layer, once it has gotten the destination, then it's going to encapsulate it into a frame. That means it's going to encapsulate it going through a transport data link layer. And the data link layer is the guy that deals with these interfaces. All right. So when the packet is received from one network and destined for another network, the router performs two major steps. It decapsulates the layer 2 frame header and trailer to expose the layer 3 packet, and then it examines the destination IP address in the packet to find the best path for the routing. So the point we're making here is that when a router receives, like here, when a router receives receives a packet that is coming from layer 3. In this case, what you can see here is a PC here is trying to generate a message, so there will be an encapsulation process. Layer 7, layer 6, layer 5. So you see these 3 layers are in purple. All right, it simply means that they all form data. The PDU is known as data, so it's the same encapsulation. So from here, the PDU is encapsulated into data transport layer, layer 4. Then layer 4 will now segment it and then add the TCP or UDP header and then send it down to layer 3. The layer 3 will now package it into packets and then send it down to layer 2. Layer 2 will now package it into frames, all right, frame header and trailer, and send it to layer 1. Layer 1 will now break it down into binary bits and format it based on the type of network media that is connected to it. So you see, by the time it is encapsulated here and it comes down through the network media, it goes to the next device. By the time it gets to the interface of the router, there would be what? A decapsulation. There will be a decapsulation, and the reason for the decapsulation is so that the router will find the information meant for it and then know what to do with the information. So this decapsulation, it decapsulates layer 1, decapsulates layer 2, and decapsulate layer 3. So why does it stop at layer 3 decapsulation? The reason is because this router is a layer 3 device, is a network layer device. So it needs to decapsulate up to that network layer device in order to for the router to be able to understand the information that is inside the IP header. So once it decapsulates it, it's basically interested in the source IP address, the destination IP address, right? So once it does that, it determines, okay, the destination IP address is this. Then it will use its routing table in order to trace the closest match to the destination where it is going to forward. So when it comes to the forwarding, it has determined where it's going to forward it. Then the next thing is to get the MAC address of that interface that it intends to forward the traffic through. So it will now give it to the layer 2 that will re-encapsulate it in that format, and then layer 1. So the re-encapsulation takes place. And then the message is now sent to the next device where decapsulation takes place to understand, then encapsulation. Then the next one, decapsulation, then encapsulation. Then by the time it finally gets to the recipient, what happens? What happens is that there's going to be a decapsulation. Now the decapsulation is going to do all the way through. All right, the decapsulation is going all the way to the layer 7 because the layer 7 is where the message is destined for. So you see here, this message here was meant for this guy. This one is meant for this guy. This one is meant for this guy. This guy is meant for this guy. All right, but look at it. This one is meant for this. This one is meant for this. This one is meant for this. This one is then meant for this. The same thing for layer 2 and layer 1. The same thing for layer 2 and layer 1. The same thing for layer 2 and layer 1. The same thing for layer 2 and layer 1. Okay. Now, how does it make its forwarding decision? Remember, the forwarding is one of the functions of the router, all right? And the forwarding is like the act of pushing the data. I have discovered this is my destination IP address. How do I forward the data? All right, that is just it. So now the router must determine how to encapsulate the packet and forward it out the correct egress interface. Now, the data link frame with an encapsulated IP address arrives on the egress interface. All right, so this is the data link header. All right, this is the data link trailer. This is the destination IP address. All right, that comes from layer 3. All right, this is the rest of the IP packet information. So the most important one is the destination IP address. So once this guy sees it, then it goes to the routing table. That it here. It goes to the routing table and checks the guy that has the closest match. It checks the guy that has the closest match. And once it checks the guys that has the closest match, then it knows how to now forward the interface. So by forwarding it, it now comes and then puts the information here and then forwards it. So the router examines the destination IP address in the packet header and consults the IP routing table, as we can see here. Okay, so the router finds the longest matching prefix in the routing table. The router encapsulates the packet in a data link frame and forward it out the egress interface. So the destination could be a device connected to the network or the next hop router. But if there is no matching route to the entry, the packet is going to be dropped. So the three actions a router can perform with a packet after the best part is actually determined is either to forward the packets to a device in the directly connected network, or to forward the packets to the next hop router, or to drop the packet. All right. So the process varies based on whether the packet is an IP version 4 or it is an IP version 6 packet. Now, what's the difference? If it is an IP version 4 packet, the router will check its address table for the destination IP version 4 address and associate it to the MAC address. All right. And if there is no match, the router sends the ARP request and the destination device will return with a reply. And then it will map it with the MAC address. Now, the router can now forward the IP version 4 packet in an Ethernet frame with a proper destination MAC address. But if it's an IP version 6, the router will check its neighbor cache for the destination IP version 6 address and associated Ethernet MAC address. But if there's no match, the router sends the neighbor solicitation message and destination device will return with the neighbor advertisement message. Then after that, the router can now forward the packet to an Ethernet frame with a proper destination. Now, if the packet entry indicates that the destination IP address is on this remote network, it means the destination IP address of the packet belongs to a device on a network that is not actually directly connected to this host network. So if there is no match between the destination IP address and the prefix in the routing table, what will happen? You will just have to drop the packet. Now, how about routing information? We have directly connected routes and we have remote routes. These are information that you can find stored in the routing table. Now, the difference is the directly connected routes are the ones that are actually connected to the interface of the router directly. All right, directly connected to the interface of the router. But the ones that are remote are connected to other routers, not directly to the router. So a routing table is basically a data file that is actually stored in the RAM and is used to store route information about directly connected and sometimes remote network. So the routing table contains network or next hop associations. So these associations tell a router that a particular destination can be optimally reached by sending the packet to a specific router that represents the next hop on the way to the final destination. So you see this router here is directly connected to this router that is here. All right, so this is directly connected routes. So the destination network entries. Now, if you look at this, for instance, you see this router 1 is connected to two different networks. This network and this network. All right, and this network is directly connected here, directly connected here, and this router is directly connected here. Okay, this router 2 is having two networks too. Can you see? Now this network is directly connected to router 1, but it is remote to who? To router 2, because router 2 is not directly connected to this network nor this network. It is just directly connected to router 1. All right, so you see, network remote to router 1. So this network here is remote to router 1. This one here is directly connected to router 2, but is remote to what? Router 1. So it is the same issue that you have in router 1. Okay, so directly connected interfaces are added to the routing table when an interface configured and active. All right, local route interface are added when an interface is configured and is active. All right, static routes are added when a route is manually configured, all right, and the exit interface is active. And then the dynamic routing protocol is added when routing protocols that dynamically learn about the network, for instance, that a dynamic protocol like AIGRP or OSPF, all right, they are identified. Now, one of the first dynamic routing protocols that is very common is RIP. RIP is Routing Information Protocol, or which is RIP version 1. All right, and we have RIP version 2 now. All right. So to address the needs of larger networks, we use other routing protocols like RIP, we use OSPF, we use ISIS, that's intermediate system. We can use IGRP, EIGRP also. So all these things that I'm circling here, they are dynamic routing protocols. And when we say dynamic routing protocols, that means they actually contain an algorithm that can help the routers to be able to communicate automatically within themselves on how to advertise their own networks to their neighbors, so that remote networks can be populated in remote networks. So they are like in this category, what we call interior gateway protocols, and then we have what we call the exterior gateway protocols. Now, when we say exterior gateway, and when we say interior gateway, what are we talking about? We're saying exterior gateway has to do with between the network and the ISP. If you have any, you want to interconnect with another network that is excluding from yours, maybe an ISP or another organization or somebody else, you want to connect your own network to another network that is not managed by you, then you use your exterior gateway. But you can use interior gateway when you are connecting your devices within your network. All right, within your network. Now we have both IP version 4 and IP version 6, and they apply for both of these. Now within the exterior gateway, we have like BGP. The BGP is the protocol is called border gateway protocol, that you use to connect from your network to another network entirely. All right. Now within the interior gateway protocols, we have what we call the distance vector, and we have what we call the link state. All right. Now the distance vector are like RIP version 2, EIGRP, RIP NG, EIGRP for version 6. All right. And then link state, we have OSPF version 2, we have ISIS, we have OSPF version 3, and then ISIS for IPv6. Okay. The primary responsibility of the packet forwarding function is to encapsulate packets in the appropriate data link frame. All right. Type for outgoing interface. So the process of packet forwarding is described through this particular example. So you see this PC1, for instance, is interested to send message to PC2, and PC1 is on an entirely separate network than PC2. Can you see? There's a one connection here. So PC1 says, because PC2 is on a different network, I will encapsulate the packet and send it to the router of my network, which is R1. The R1 is the guy that actually is the border for this network. So let me find that address. So what is he going to do? PC1 will send a packet PC2. The first animation, PC1 sends the packet to PC2. Note that if an ARP entry does not exist in ARP table for the default gateway of this, PC1 will send the ARP request. So this guy sends, this is the gateway, 192.168.1.1. You understand? So this is the gateway, and then from here it's going to now populate the information in the packets. All right, so it's going to now send an ARP to find out what is the IP address of PC2 of my destination. So once he finds the IP address, then he's going to come and include it in the destination. All right, now once it does that, look at it, we populate it in the destination here. My ARP table tells me that PC2 uses a MAC address of 0B31. So you see, you will now pick the 0B31 and put it in the destination MAC address segment. Okay, so we have a destination IP, we have a destination MAC. So you see, the destination IP is the IP of this particular machine, but the destination MAC is not the MAC address of this machine. The destination MAC is the MAC address of the next hop, which is this guy here. Can you see? Is the MAC address of the next hop. So once there's going to be encapsulation and decapsulation again, the destination IP address will not change, but the destination MAC will change to this guy here. You understand? So it is at this point that you will get the destination of this guy here. So R2 now forwards the packets to R3, which is to this guy. So this is a point-to-point serial connection, so no source address is required. So from here, it's going to now send it. So as the exit interface is not Ethernet network, R2 does not have to resolve the next 4 address with the destination MAC address. So when the interface is a point-to-point serial connection, the router encapsulates the IP version 4 into the proper data link frame format used by the exit interface. So as there are no MAC addresses on serial interfaces, R2 sets the data link destination address to an equivalent of a broadcast address. So remember what we're just doing, we're thinking of how this message is forwarded from here to here. So at this point here, we are here. So my IRP table tells me that PC2 uses the MAC address of this 20. All right, so that is the MAC address of this guy here. All right, so but if you observe that the destination address does not change. All right, now those are end device. Intermediary devices, we said they are devices that actually controls the flow of the traffic or enhances how they move around. So we have something like a hub, we have a bridge, we have a switch. So these ones are basically layer 2 devices. This is like a layer 1. These are like layer 2 devices. Okay, so the Ethernet hub acts as a multi-repeater, all right, that receives incoming electrical signals, and then you can take them out, re-amplifies them and takes them out. Bridges have two interfaces, all right, and are connected between hubs to divide the network into multiple collision domains. You see, in a hub, irrespective of the number of ports that are in a hub, it is a single collision domain. But in a bridge, each port in a bridge is a collision domain. It's the same thing that goes on with a switch. So the bridge have two interfaces and are connected between hubs to divide the network into multiple collision domains. So each collision domain can have only one sender at a time. Okay. So LAN switches are multi-port bridges that connect devices into a star topology. Switches also segment a LAN into separate collision domains, one for each switch port. A switch makes forwarding decisions based on Ethernet MAC addresses. All right, so like you have in a switch, it has multiple ports, and each of those ports is a collision domain, which means that each of the systems connected to these ports can send a message at the same time. So if there are 10 ports here, 10 messages can go at the same time. All right, the same goes to the bridge. But for the hub, if there are 10 ports here, all of them are just one collision domain. So only one device can send message at a time. Now, if more than one sends, there's going to be collision. All right, that is that. Now, a switch uses MAC address to direct network communications through the switch. So to appropriate ports, so and forward the destination. A switch is made up of integrated circuits and accompanying software that controls the data path through the switch. So for a switch to know the port to transmit a frame, it must first learn the device existing on each port. So as the switch learns the relationship of the ports to device, it builds a table called the MAC address table. So the MAC address table is going to map the port of the switch to the MAC addresses. All right. Sometimes it is called content addressable memory table. All right. Now, LAN switches determine how to handle incoming data frames by maintaining the MAC address. So the switch uses the information in the MAC address table to send frames destined for a specific device out of the port to which the device is connected. So the following two-step processes is performed, all right, on Ethernet frames. First, the learn process, and the learn process is to examine the source MAC address. Now, the point we're saying here is that, you see, this is a MAC address table. Port 1 is tagged or mapped to a MAC address 0008, and that's the MAC address of PCB. Port 2 will be mapped to this. Port 3 will be mapped to this. Port 4 will be mapped. Now, that is the information that you can find in the MAC address table. But sometimes the MAC address table might not have all this information. All right. So if PC1, for instance, wants to send a message to PC-C or PC-D, the question is, how will it know the MAC address since it has not been mapped? It says, I do not have this source MAC address and the incoming port in my table, so I will add it. So what it does is that if the source MAC address is not in the table, it is added to the MAC address table along with the incoming port number. So it sends a broadcast. Once it sends a broadcast, it comes, enters here, it comes, enters here, and it comes, enters here. So the guy that is going to respond to the broadcast, okay, the guy that is going to respond to the broadcast the MAC address and the port number will be added to the table. So if the source MAC address does exist in the table, the switch updates the refresher timer for that entry. By default, most switches keep an entry in the table for 5 minutes, after which they will now update it. Okay. Now, if the destination MAC address is a unicast address, the switch will look for a match between the destination MAC address of the frame and the entry in the MAC address table. All right, that is what we are seeing here. So once it sends the broadcast, it comes to B, comes to C, it comes to D. So the guy that responds, all right, if the destination MAC address, the MAC address is in the table, it will forward the frame out through that particular specific port. But if it is not, it's going to. So if the destination MAC address is a broadcast or a multicast, the frame is also flooded out of the ports. Right? VLANs. What is a VLAN? A VLAN is a virtual network. And what does it do? It provides network segmentation. All right? It provides network segmentation and organizational flexibility within a switched internetwork. That is what a VLAN does. So it allows an administrator to segment network based on factors such as function, project team, applications, without regards to physical location. For instance, this is an office building and it has 3 floors. All right, it has the ground floor where the server room is, then it has the first floor, the second floor, the third floor. Now, in the first floor, we have departments like human resource, sales, and information technology. We have the same group of people in the second floor, and we have them also in the third floor. So the concept of VLAN is irrespective of their location, what we can do is we can logically group all the computers in IT under the same network. All right, they will get the same block of IP address, they will have the same set of broadcasts, they will have the same set of information, they will have a lot of things in common, and interestingly, they can communicate within each other. Okay, now we can do the same for human resource, we can do the same for sales. All right, that's a very good part when it comes to VLANs. Okay, STP has to do with spanning tree protocols. Now, spanning tree protocols is actually used to maintain a loop-free path. Now, what is a loop-free path? You have maybe a switch here, you have another switch here, you have another switch here, and probably you have done all this for redundancy. Okay, for redundancy. Now, if this switch is connected to this guy, this is connected to this guy, and this is connected to this guy, be rest assured that if there is a broadcast that is sent here, it's going to go throughout all the ports, including this guy. Then this guy will go out all through the ports, including this guy, and then it continues. So it becomes a loop like this. It keeps going round and round, and by the time it's going, it consumes bandwidth, it creates bottleneck, and then it can cause a lot of problem on your network. So STP, spanning tree, is meant to identify this kind of network, or where there is a loop, and then it just blocks one of the redundant ports just to make sure that there is no loop. So loops and duplicate frames have severe consequences in a switch network. So STP was developed to actually address these particular issues. So it ensures that there is no one logical path between all destinations in the network by blocking redundant paths. So a port is considered blocked when user data is prevented from entering or leaving that particular port. All right. Now, multi-layer switching. Now, on the OSI model, we know that the switch operates at layer 2, okay, which is the data link layer. But there are switches that can operate at layer 3. You know, layer 3 is where routing takes place. So if we have VLANs within a particular switch, I have a switch, I have VLANs here, I have another group of VLANs, I have another VLANs, I have another VLANs. So for these VLANs to communicate with each other, I need a router. So if this VLAN wants to communicate with this guy, the traffic has to come to this switch, then go to the router, then the router will route the VLAN out to come to talk to this guy. Now, a layer 3 switch is saying, okay, yes, you might have a router, all right? You might also have a switch that has VLANs, okay? Now, if this switch is a layer 3 switch or a multi-layer switch, this VLAN, if it wants to talk to the next one, it will just cross here. It doesn't need to come to the router, thereby trying to, here there will be a lot of overhead or traffic on the router interface here. Here it frees the router from that, okay? So all Cisco Catalyst multi-layer switch actually supports the types of layer 3 interfaces. So it supports the routed ports and it supports the switch virtual interface. The routed port is actually a pure layer 3 interface similar to the physical one on a Cisco router. And then a switch virtual interface is like a VLAN interface for inter-VLAN routing. In other words, SVIs are the virtual routed VLAN interfaces. So this is a multi-layer switch. See it here, meaning that it can serve as layer 2 and it can serve as a layer 3 and it can do routing. Okay, so a routed port is physically a port that acts similarly as a router. So unlike access ports, a routed port is not associated with a particular VLAN. So it behaves like a regular router. So also a layer 2 functionality have been removed. Layer 2 protocols such as spanning tree do not function on a routed interface. So some protocols such as LSCP and Ether channel do function at layer 3, unlike Cisco IOS router. All right, routed ports on a Cisco IOS switch who does not support some interfaces. All right, so like here you see you can have your Ether channel here. Ether channel is when you have multiple physical links using multiple cables and then you aggregate them to have a bigger bandwidth. Okay, you can see Ether channel here, you can see Ether channels here, you can see Ether channels here. So you want to increase the bandwidth or the speed. All right, so you can use Ether channel. Now, you see, the conventional way of doing this inter-VLAN routing, you have VLAN 10 and VLAN 20, is that this guy comes here to the router and is routed here. Meaning that on this router here, you have to create what we call the sub-interface. The sub-interfaces, all right? The sub-interfaces that you create here to communicate with each of the VLANs. But you see, in a layer 3 switch, all right, insert this multi-layer switch serves as the router in this case. All right, so an SVI is a switch virtual interface where you can just do it here. Unlike the basic layer 2 switch, a multi-layer switch can have multiple virtual interface, switch virtual interface, all right, and can be created as for any VLAN that exists on the switch. Now, when you have a router, it's not advisable to have more than 30-40 VLANs on one interface. You would have sub-interface. You have to think of a way around it. But with a multi-layer switch, that's not a problem. So an SVI is considered to be virtual as there is no physical port designated or dedicated to the interface. It can perform the same functions for the VLAN as a router interface and can be configured in much the same way as a router interface. So the switch virtual interface for the VLAN provides layer 3 processing for the packets to or from all switch ports associated with the VLAN. Now let's look at wireless communication. Remember that when you're doing wireless, you are talking about connecting end devices without a cable, using radio waves or radio frequencies. All right. So wireless LAN connects to clients to the network through a wireless access point. All right, it's a device that beams out wireless beacons where the clients will actually connect to. These are like one of the differences with the normal LAN cable. So the wireless LAN connects mobile devices that are often battery powered, right? Wireless supports hosts that contend for access on frequency, radio frequency media. Wireless use a different frame format than wired Ethernet LANs. And then wireless raise more privacy issues because radio frequencies can reach outside your facility. All right. So those are some of the differences. So let's look at difference between wireless LAN and wired LAN. Like we see here on the physical layer, in wireless LAN, we have radio frequencies, all right? And then in wired LAN, we use physical cables to connect, all right? In media access, that is you want to connect to a media, it runs a protocol collision avoidance, and then while Ethernet runs collision detection, all right? And then in terms of availability, wireless, anyone with a wireless network interface card can access the access point. Whereas in wired, you have to physically connect a cable. All right. Now, signal interference exists in wireless, while it's very minimal in cable. And then regulations, basically, there are different regulations by the country you exist. In US, it's a different regulation. In Nigeria, it's a different. In Europe, different. But in cable, they just work with IEEE standards. Now, the structure of the frame in wireless is similar to that of the Ethernet. Because we're talking about the frame control, then the duration, then address, then sequence control. So you see the header has the header information and the frame check sequence. Then you have the payload. So it's the header information that now is broken down into this. Now the duration is used to indicate the remaining duration needed to receive the next frame transmission. That is what the duration. The frame control actually identifies the types of wireless frame and contains the subfields for protocol versions and stuff like that. The address 1 and address 2 actually contains the MAC addresses, of the receiving device and MAC addresses of the transmitting device as well. Okay. Address 3 contains the MAC address of the destination device. And then sequence control actually contains information to control sequencing, all right? Address 4 is usually missing as it is used only in ad hoc modes, all right? The payload contains the data that is being transmitted, and the FCS, which is excuse me, the frame check sequence, It's basically used for layer 2 error control. Now, the wireless has what we call carrier sense multiple access collision avoidance, while the cable is collision detection. Now, what is it? It's actually a way to avoid traffic collision. All right. So wireless LAN are half duplex shared media configurations. And half duplex means that only one client can transmit or receive at a particular moment. Shared media means that the wireless clients can all transmit and receive at the same radio channel. And this kind of creates a problem because wireless clients cannot hear while it is sending, which makes it actually impossible to detect a collision. So to resolve this issue, they have to use carrier sense multiple access with collision avoidance to determine how and when to send information or data. So a wireless client actually does the following, which is listens to the channel to see if it is idle or busy before it sends a message. Then it sends a ready to send message, which is the RTS, and it sends it to the access point to request dedicated access to the network, and it receives a clear to send message, which is the CTF, from the access point, granting access to send whatever message it wants to send. If the wireless client does not receive the clear to send message, it will actually wait a random amount of time before it starts the process all over again. So after it receives this clear to send, it retransmits the data, and all transmissions are basically acknowledged. All right. So for a wireless device to communicate over the network, it must first of all associate itself to an access point or an access router or a wireless routing. All right. And the important part is the protocol standard that governs it is the 802.11 standard. And how does this takes place? The wireless process completes by first of all discovering the access point. Maybe you have this laptop here. You check the wireless, and then it sees the access point name, and then it makes an attempt to connect, as you see here. Makes an attempt to connect. Now, then this guy, if there's a password or something like that, then you enter the password. Then this guy authenticates the device. Then once it does that, then it will fully associate. Right? It's when it associates that you can begin to send information. So for you to be able to connect, there are certain things that you must need. Number one is the SSID. The SSID is the service set identifier, and it's actually a name that you give to, like a beacon that you give to the access point, and you will see it in the list of your available wireless list on your laptop or your mobile phone. So the password is required from the wireless access point to actually authenticate the protocol. Then the network mode actually refers to the protocol standard, whether A, B, G, N, AC, or AD. Now, all these ones are the protocols. So if your system is only 802.11.8, if the router is only 802.11.8, that means only 802.11.8 devices can connect. So these ones describe the wireless standards that devices can be used to connect. So the security mode refers to the security parameter settings such as like the wireless encryption protocol or WPA, wireless personal authentication or WPA2, and they always enable the highest level of security supported. Then the channel settings refers to the frequency or band that this transmission will hold. Usually channel 11, 1, 11, and 6. 1, 6, and 11 are free. I think so. They're usually free. The others are not, so it can move around. Wireless devices must discover and connect to an access point or wireless router, and then wireless clients connect to access points using scanning process such as passive and active. So you see the access point is going to generate the beacon SSID and then the supported standards and the settings. All right, and this guy, if it meets the requirements, and then it connects. So the passive mode, in this mode, the AP openly advertises its service by periodically sending broadcasts. Broadcast beacon frames containing the SSID, supported standards, and security settings. So the primary purpose of the beacon is to allow wireless clients like laptops, mobile phones, and stuff like that learn which networks and APs are available in a given area. So this allows the wireless clients to choose which networks and APs to actually use. So the active mode. In this mode, the wireless client must know the name of the SSID. So the wireless client initiates the process by broadcasting a probe request frame on the multiple channel to include the SSID name. All right, so sometimes you do what they call the hidden, all right, hidden SSID. So you have to type the name on your system, and that's what is going to be requested. So the APs configured with the SSID will send a probe response that includes the SSID supported standards and security settings. So active mode may be required if an access point is configured to not broadcast the beacon. So like I said, sometimes if you don't broadcast the beacon of SSID, that means you are doing it in a hidden mode. So if you're doing a hidden mode, that means you have to physically come to this laptop and configure the SSID of this AP before they can start the process of configuration. So a common wireless data implementation is enabling device to connect wirelessly via a LAN. So in general, a wireless LAN requires wireless access points and clients that have wireless network interface cards. So you see, this is like a wireless router. It's like a wireless router, and this is the antenna. These are the Ethernet ports that you will connect to your network where you're going to use to enter. So this is like the one aspect. So in a home and small business, wireless router actually integrates the function of the router, switch, and access point into a device shown. So you see, this can be like your switch, and then you can, so that means you can connect LAN, one PC, connect another one, connect another one, connect another one. Or you can connect and allow this guy to do wireless for you. Okay. So all the control and management functions of the access points on the network can be centralized into a wireless card controller. All right, wireless LAN controller, meaning that you can have what we call a controller-based access points or a standalone autonomous access points. Now, the standalone autonomous access points do not need a controller. On their own, you can configure them and they will manage themselves. But the controller base means that you would have to have a controller somewhere that all the APs would be communicating with. So all the configurations or settings you make on the controller, that's what will be applied on the earpiece. So when using a wireless LAN controller, the earpiece no longer act autonomously. All right, they no longer act, but instead they act as lightweight earpiece. All right, so lightweight earpiece only forward data between the wireless LANs and the wireless LAN controllers. So all management functions such as defining SSIDs and authentications are conducted on the centralized controller. So the controller will be able to control all the configurations of the APs. So in summary, what we have looked at is that for you to be able to communicate with on a network, you need your end devices, you need your intermediary devices, and you need your network media. And the end devices, we said, basically those are where you generate your traffic, or the receiving end. They're like the destination of the devices, traffic. All right, and examples are like your servers, your laptops, your desktops, your IP cameras, your fridges, any of those devices. And we said that they all have unique IP addresses that actually help to ensure that there is no conflict, and it helps to identify them. The intermediary devices we discussed, like the routers, the switch, the bridges, the hubs, actually functions in the data link and the network layer. That's layer 2 and layer 3 of the OSI model. And in most cases, they are multi-port inter-network device where they help to control the flow of the traffic and things like that. We said the router actually helps us to determine the path it takes to for the packet, and it does also forwarding. All right, and it keeps all this information in the routing table. And the switch, we said we have a multi-layer switch, which is a layer 2 switch and a layer 3 switch, that where we can create our VLANs to help segment our network, and it keeps the MAC address table and things like that. And then we also talked about the wireless, which is like the media. It helps us to communicate wirelessly without cable, and we discussed these differences and the advantages. All right, so that will be it for today's class. Our next class is going to be next tomorrow, and don't forget to sign your attendance for today's class. So thank you for attending. Have a lovely day.